Hello world, Servus Wien, and welcome to Pattern-Based C#. Today, Stefan and I are going to take you on a whirlwind tour of C# language patterns.
Patterns?
Yes.
Do you mean something in the term of pattern matching, where we can check our instances against a more or less complex pattern, and if it returns true, then it would print this to the console?
Not quite. So pattern matching is a pretty cool subject, but not the one we're covering today, because pattern matching is about checking an expression for specific characteristics, just as Stefan just showed. But we're going to be talking about compiler-recognized patterns. So language features that don't rely on interfaces or inheritance, but rather on a type's shape.
The compiler.
Yes.
So you're saying something like the dynamic keyword, which whatever hides at runtime behind that, we can foreach it either way?
Kind of, but dynamic does allow you to bypass type checks at compile time. And we're going to be talking about type-safe patterns of the C# compiler. So yes, we will make our own custom type foreachable in this talk, but we'll do it in a compile time checked fashion. Yeah.
So I see, right, because actually at runtime now, behind this dynamic, we have an int. We can't quite for each an integer, so we get a runtime exception. So are you saying that we could, for each our talk type, even though it doesn't necessarily implement the IEnumerable interface?
Absolutely, we can and we will, just in a little bit. But before we get into the code, we've got a little something for you to make things fun and interactive. So I need you all to take out your phones right now and scan this wonderful QR code right here. It will take you to a really, really cool quiz, and which will give you a chance to win some pretty awesome prizes and also bragging rights for the entire evening. So you don't want to miss out on that. Just follow the QR code. There are a couple of questions. If you don't know the answers straight away, don't worry. Everything is directly based on what we'll show you today. So just follow along and you'll learn everything you need to answer the questions and win those awesome prizes.
At the very end of the quiz, you also find, after you submit it, you find two links. One is leading to a GitHub gist, if I'm pronouncing that correctly, leading to our socials, and if you want to connect later on, and also to that aforementioned Sentry key, if I want to give Sentry a try.
Absolutely. All right. And I guess with that, it's time to maybe introduce myself a little bit more. Hello, my name is Eva. I'm a software engineer. And my journey to software development was actually not super linear. I actually did a bit of a career change a couple of years ago, right around the time when I joined Stefan on his live stream. And the one thing that really helped me learn, especially at the beginning, was, well, for one, having a great teacher, but also to have a look behind the scenes at what's really going on there. And that's exactly what I'll be doing with you today. So I'll be the one looking under the hood to show you how the compiler actually thinks. So what is it looking for? What patterns does it recognize? And how can you teach it new tricks? So whether you're new to C# or have been around for a while, I hope this talk helps you see the language in a new way and gives you the confidence to dig deeper.
And I will be Eva's coding agent. She will prompt me and I will implement those patterns, hopefully also shifting all of these ducks to the right-hand side, so I take ownership. Hello. Yeah, already mentioned, now I'm wearing the other hat. I'm Stefan, Microsoft MVP, JetBrains community contributor, and also organizing this very meetup. And it's always exciting to stand on the other side of the camera, but also terrifying. Yes, as mentioned before, for completion, I am here at Sentry. I guess that's enough of that. Yeah.
Well, as we already mentioned, and I pressed the wrong button. I'm just going to go here. Is that it? No, that's the wrong one. You do it.
Excuse me.
As you already mentioned, Stefan and I have a live stream. It's called To Code or Not to Code, and it's a bi-weekly excuse to code together. Well, sometimes we code, sometimes we just debug for hours, as previously mentioned. Sometimes we go on ridiculous tangents, but we always have fun. We always learn a thing or two, and every now and again we build some really cool stuff. And I'm not just saying that to advertise the stream. I'm also saying it because this talk actually came out of one of our episodes where we built a source generator that lets you deconstruct any type. And I'll show you what that means in a second if I find the correct buttons. Woohoo! All right, so what have we got here? We've got our talk class. we've got 3 accessible properties right there. Oh my goodness, this is on an angle, so this is exciting. Right, and maybe this helps a lot, actually. Thank you very much. You can also see a little attribute here that might seem unfamiliar. That's because that's from our source generator. And let me just get rid of this. So up here, this should look pretty familiar. We create a new instance of our class. And now this is where it actually gets interesting. So this is a deconstruction syntax. On the left-hand side, we declare a tuple of variables. And on the right-hand side, we've got the instance of our class. And once the deconstruction is complete, you can actually use these variables just like any other local variables and, for example, print them to the console. Right. Okay. So actually, let me try out if this works. That would be hilarious if not. So I'll run this. And then we'll wait and do a little dance. This is where the cartwheels come in that I promised. I did press the right button, did I?
Yeah. It's just,
okay, perfect, amazing. Wow,
it's my laptop. This is of older age.
Yeah, but you can see we get the right stuff printed to the console. And so, yes, this works actually wonderfully. Now, as promised, let's have a look underneath the hood. For that, I'm going to go to the IL view, and I'm going to go, and this also moved. This is exciting, to low-level C#. Yes, and is this? Yes.
It is interesting. Where we use this very laptop for our test as well, and it was faster. I don't know. Maybe it's tested Tuesday blues. That doesn't make sense.
It absolutely is. Well, in that case, this talk will be about 2.5 hours. So be prepared. I hope you brought snacks. I'm only kidding, of course. So here we can kind of see what really happens underneath the hood. And we can see that we call a method called deconstruct on our talk instance. And we can also see that it does have these corresponding out parameters from the variables that we also want to print to the console. And this is actually what our source generator emits. And if you don't have that, you actually cannot deconstruct your type. I'll prove this to you. If I can close this window. Okay, I'll use my mouse. I'll prove this to you when I just remove our source generator attribute right here. And you can see we no longer compile because the compiler doesn't know how to take our object apart, because as soon as the compiler sees the deconstruction syntax, it is looking for this method called deconstruct, exactly deconstruct. It has to have that name, and is checking whether it has the corresponding out parameters. Fun fact, a record class can do this out of the box. And so, as chance would have it, we do have a record right here. Who would have thought? I'm going to put that in there. You can see it compiles. I can also run it, maybe. Should we just? Oh, yes. OK, this was a lot quicker. Perfect. Hopes are rising. And if I go to the IL window again, and if I scroll a little bit to the right, I can see that we again call deconstruct right here. So we're doing the exact same thing. Yeah, as I mentioned, the compiler is looking for this method, and as long as it finds it, it knows what to do. And it doesn't care whether a source generator emitted this method, whether you're using a record which does this out of the box, or whether you add it manually. And because it's a pattern, and this is actually our very first pattern. Now, for argument's sake, let's say that you do not want to use a record. You want to use a class. And you also don't want to use, the source generator that some weird people wrote on a live stream. So what do? Well, this does not compile. And you can actually see the error says no deconstruct method with 3 out parameters found for the type talk. So, Stefan, can you manually add this deconstruct method? Because if you do it just right, the compiler should think if it looks like a duck, swims like a duck, and quacks like a duck, it probably is a little deconstruction duck.
You are absolutely right. Okay, so just as Eva has decompiled, we need to provide a method called exactly deconstruct. The method is void deconstruct, and now we add an amount of out parameters that we need in order to fill in these local variables declared in a tuple. So we have 3 out variables here, so we need those 3 outs. String title, string meetup, and also the datetime offset for the start. I'm gonna copy this here, add the out modifier to all of these parameters. And by providing this, we already see the exception or the compiler error up here is going away. So the compiler is already binding to this deconstruct method. Now I declared this as an instance method. I could have also declared this as an extension method. Not every pattern, but most patterns, or those compiler recognized patterns, you can provide as either an instance method or an extension method. If you have both, just as with every compiler binding phase, instance methods are usually preferred over extension methods. Also, I'm making this public here. It needs to be accessible from the call site, just as what the compiler is lowering the code to. So in our case, this could also be internal because we are in the very same assembly, but for simplicity for this talk, we make everything, all types and members public for today. All right, now we got an compiler error here because whenever we use out parameters, they need to be definitely assigned in this method. Let's do just that. So we'll assign the title to the actual title of the instance. Same for the meetup. And same for the start. And now when we run this code, it should work just as it was working before. We just now manually implemented it and didn't get it auto-generated by the record or by our source generator. The source generator was providing this as an extension method under the hood. There we go. Now we can also overload deconstruction, not by type. So we couldn't vary by type. We can only vary by amount. So let's say I want to deconstruct into only the title and the name of the meetup. Now the compiler gives us another hint. No deconstruct method with 2 out parameters was found. So all we're going to do is duplicate this method, remove the third one so that we are just left with 2. Can remove that. And now the compiler, since we deconstruct into a tuple of 2, we now bind to the deconstruct that has 2 out parameters. And I believe I've earned myself the very first duck.
I think you did. Awesome. Well, first pattern down. All right, let's have another really, really simple example. I'm going to get rid of everything. And then I'm going to, oh, that was funny. Did anyone else see that? No, you all looked, oh, God damn it. All right. Oh no, what did I do? Anyway, this is also not int. I'm struggling. Wow. It's been a long day. That's all I've got to say for myself. I'm going to create a list of int, and I'm just going to initialize it just like this. I'm scared. It's also because it's slightly lagging. Okay,
it is slightly lagging indeed. Yeah.
It's not as easy as it looks. I just want to say that. So I initialized a list here, and just to make it more visible, yes, I'll for each it. And in list, and I'll console right line it to the console. All right. Temp. Okay.
You have int instead of item. Yeah.
Item. Oh my goodness, it's a tough day. It's a tough day, everybody. I'm gonna do this. It's difficult. Okay, but we did get there in the end. So now we know that we can for each a list. Or do we? Or can we? I don't know. Let's run it. Let's see. So this next pattern is about collection initialization. And yes, it's a very complicated code. Tough to write. Okay, we've got some technical difficulties today, everybody. But we did manage to print all the items to the console in the end. So well done. Now let's, as promised, have a look what lies underneath. I'm going to go to my trusty IL view here again, and I'll see that underneath the hood, we create the list, and then we call add once for each item in the initializer, and that's our next pattern, actually. So, for example, if I have my own list type, so I can duplicate this here, and this will make things a lot easier. And also, let's not have 0, 2, 4. Let's have maybe 5, 6, 7, 8, 9. And let's create this type. I'll also use this. Wonderful. So you can see now this does not compile. And when I hover the error, I can see cannot resolve symbol add. So again, the compiler is looking for our type to match the shape that it is looking for. So the add method in this case. And this is where Stefan comes in. Can you make our list quack like a proper collection initializer?
Sure, I can. Hope I can. This would be terrible if I wasn't. All right. Now we actually don't have one error, but two errors. One error is complaining about the missing add. The other error is complaining that the our list needs to implement for collection initialization to work the IEnumerable interface. This is because for collection initialization to work, the collection that we want to initialize needs to be the type needs to be a collection-like type. And this is done by making it implement IEnumerable. Now let's add the add method. And the add method, since we have a generic list, takes a t. And from the call side, now the errors have already disappeared. Now we just need to get the implementation right. So let's add the missing interfaces. Let us, as an implementation detail, I will resort to the existing list. But it is just an implementation detail for our code to actually work. And let's here just add to the underlying list. All right, let us get the delegate to the list. Oh, this should be generic, of course. And I believe there is one more interface missing. Delegate this one as well. So we're gonna delegate the implementation details of the interface just to the existing list so that it works. But from the compiler perspective up here, it doesn't see through implementation details. Seeing through implementation details is the runtime's job. The compiler just sees the public surface area. It's a type that's IEnumerable. It has the f method. Hence, I now call 5 times the add method. And when we iterate through this very collection, we should now get 5 through 9.
Awesome. And since, well, we can also initialize dictionaries. And since a dictionary is basically a collection of key value pairs, do you think we could overload the add method to take 2 values?
Let's give that a try. I'm going to add a bit of new lines here to make it more apparent. What you can always do also with singular items, just add braces. Come on. Yes, I'm mixing up shortcut. Yeah, I'm mixing up shortcut. I'm on my day job on a Mac and now, oh yeah.
We have all the excuses ready, don't worry.
So how can we control it for? There we go, yes. Okay, let's do it manual. Braces.
Pizza. Okay.
So this is the same behavior as if we were just having them without these braces. We see that Ryder is already mentioning that these are not necessary in this case, but if we want to add more than just a singular item per addition, we need those braces. And we could now say, for example, here 6 and yet another 6. And now we get a compiler error saying, okay, the add method only has a singular parameter, but it was invoked with 2. So the compiler is now searching for an add that actually takes 2 arguments. Let's provide just that. Let's duplicate this add. Let's add a second argument to it. And the compiler now is happy. And this is essentially how collection initialization with a dictionary is happening. It has an add method that takes the T key and the T value, and with that enabling collection initialization.
Amazing. Oh, and everything is gone.
I was hoping to, I didn't Control C. Yeah, oh yeah, Control Z. This is not working as we planned on Saturday, right? There we go.
No, it's fine. We're fine. All right. And something that, the IDE also wants me to do it is obviously not to initialize my list like this, but to use collection expression. And I'm very happy to oblige the IDE here. Because first of all, it looks cooler. And also I can see our list also has this as a suggestion. So yes, let's do that. Wonderful. So we already look much, much cooler, but this also does something different underneath the hood. This time I'm just going to try and build, so maybe we can save some time. All right. And then I'm going to look under the hood. Okay. And we can see that for the list, even though they look exactly the same on the left-hand side, for the list, we now use a stack allocated span and use it to fill the list in one go, which is really, really cool. Unfortunately, our list, even though it looks cool on the left, it still does this thing where it creates the list and then calls add each time, which is not ideal because it could potentially grow the underlying array of the underlying list. So at the beginning, we get an array of 4. And then when we add the 5th item, we get an array of 8. And we have to copy the values over. And this is just not ideal. And I don't want that. So Stefan, this already looks pretty cool. But can you please update our list with this span-powered collection expression?
Absolutely. I really love spans. Well, sometimes maybe even a little bit too much. All right. we see, yeah, it's already working. The compiler is using the adds as a fallback, but they are not as performant as it could be. We could take a look at the implementation of list, but we won't find that, what we're actually searching for right now, because list, that's part of the core library, and the compiler, Goslin, is very well aware of the shape of the list type. So the compiler knows exactly how to most efficiently initialize lists. What about custom collections? How can we teach the compiler how to most efficiently one-shot initialize custom collections? We can take a look at the immutable array. Immutable array is not part of the core lib, I think. So the compiler does not have intrinsic knowledge over the shape of this type. It's just a type. When we take a peek at the immutable array, we will see it has this attribute, the collection builder attribute. And with that collection builder attribute, we can teach the compiler of how to best one-shot initialize any collection or collection-like type. It takes 2 arguments. One is the type where this one-shot creation method is found at, and the name of the method that should be invoked, passing a span into it. So let's provide just that. Onto our collection, we will add the collection builder attribute, taking 2 arguments. One is the type, where this method will be found. This type cannot be generic currently. May change in the future, but currently this type must be non-generic. So we can't put this static method on our generic list. We need a separate type non-generic to do that. And also we can pass the name of the method that should be found on that type. You can just say create, or usually the best practice is you use the name of operator and say our list.create. Usually it's a bit of a best practice to call these methods create. Now let's add this new type, public static class our list, non-generic, and the public static, not void, but actually what should be created, our list. So this is an our list returning method called create. We create a generic list, hence the method should also be generic. And as an argument, we pass in the read-only span. So the compiler is building up this read-only span for us then to use to initialize our collection. And after providing this method, we can scroll up and should see that this goes away, and it says, did I make a mistake? Generic, generic, generic. Well, maybe let's implement it. Let's see. Maybe it needs to update. So let's get the implementation right as well. Let's return a new instance of our list. Passing in the span. So we need to provide the respective constructor. That is taking that very span. Oops. And let's just fill our list as an implementation detail with an add range with set span. And now I was hoping this to go away, but it quite doesn't. Our list does not contain an accessible create method with the accepted signature. Our list to create. Why does it? Yeah, why does it say object? Interesting, because well, we are generic here, generic, generic. I don't see the problem. No, the generic, the create has to be generic. The type. You were promising that we're gonna do a lot of debugging, right?
Yes, we were.
Read only span of T. There we go. I don't fail to see the problem. Is this a wrong read only span? It is the BC house read only span. I'm gonna do.
Do we have a cheat sheet?
Actually, yes, but it, no, this should be it, because it says. Where does it say it's an object? I don't know where the object is coming from. Those are integers.
It's an object.
Yeah, but it's just our list. But our list of int. Yes, please. And we're passing in an integer. And why does it say object? That's very interesting. Okay. Damn it, I don't know. That's the create method. What are we missing? That's the pattern. Let's just briefly check immutable array, because immutable array works the very same. Is the Are there follow-up demos based on that? Because that would be embarrassing.
Yeah.
Damn it.
Well,
in worst case, we fall back to a collection initializer.
Exactly. We don't necessarily need the cool span, but it would be nice.
Yeah, it would be indeed. I'm quite uncertain.
You can just add it.
Something is off with our compilation.
Restart ID.
Well, maybe. Because if you take a look at the because immutable array works essentially the same. It's also a generic collection. So there is a non-generic immutable array type with the create method. And that very create method, if we were allowed to navigate to that, should look the very same. Somewhere there is the read-only spam. Yeah. So we have a public. Yeah, but it doesn't need. Oh, does it need to be params? Okay. How did we miss that? We never did. Did we do params?
Really?
That would be embarrassing.
No.
No, because the params is not necessary. Yeah. I'm afraid
there is a comment in the chat that you have something like where T.
No, I don't think we need a generic constraint. Where T, or do we have something in our code bed? Let's create collection builder. No, I'm afraid I don't see the.
Where's the cheat sheet? Is this a cheat sheet? I can't read the cheat sheet.
Yeah, I can read the cheat sheet. Time on that. Public, static. Public, all is public, all is static. Return our list of T. Yeah, I'm afraid I really don't know what the issue is.
Okay, no span power today.
the-
Then we'll just.
The only difference, but the argument name is. Oh, damn it! Yeah, I didn't earn this duck. Excuse me. This should work exactly as it is. I am quite uncertain what's going on. Excuse me. That it's trying to get something. Oops.
Wow.
Trying something with object, but yeah, we don't have object. We have integers here. We can even say integer, but it's still trying to go for object, which I am. But we are generic. We don't have object anywhere, do we? Yeah, I'm afraid this should work like that. So yeah, this would now, as is our demo, now we would see that the compiler is creating some very specific implementation detail, because the compiler actually is, if the connection initializer is constant, such as 0, 1, 2, 3, 4, those are all constants. So the compiler is creating a an inline kind of memory section in the assembly, having a reference to that, and then using that to pass that as a span, as a read-only span, for us to initialize our list. But yeah.
All right.
Not today, so it seems. Fair point. Mm-hmm.
Oh,
that's
nothing.
freezing.
It's frozen.
No.
It's your fault. We've got another excuse. Yes.
So if we put it on a different type and just create 1, 2, 3. No, it's still. Oh no.
Ooh.
How will this be? Is this not found? This found. Yeah. Sorry, I'm quite uncertain what is going wrong here. But yeah, so let's fall back to a right, yeah. That is a great idea. Let's give that a try. And
Oh yeah.
they shouldn't matter, because the params is only for if you actually directly invoke it. That's very interesting.
Yeah. Any more ideas? Extra points on the quiz.
Okay, no. Wow, I don't know. That's fantastic.
Let's go back. We already a little bit lacking. It doesn't matter that we don't have a span there.
But this should not. Yeah, this should not have created.
Woohoo!
Why is this an error? Yes, very good. Yeah, very good. There we go. Yes.
Oh, other way. Yeah.
Perfect. Okay. Cool.
Yeah, I think that's good. That's good enough for me. What are you doing?
I am getting embarrassed now. All right. So yeah.
Oh my God.
Oops.
What? Ah!
Sorry. 2, 4.
Cool.
Okay.
Yes, we're back.
I will give this duck back. Yes.
Yes. This back goes away, because now, well, let's go back to basics. Tab. I press tab. Do I have to write it? I think we have some quite. Oh, it's frozen again.
Mm-hmm.
So the next pattern is about accessing the individual members of the list. Oh.
I'm trying to shut some stuff down.
Yeah.
Let's close some tabs. Yeah, this is. I guess.
Oh,
okay,
yeah.
this machine
Actually,
is not suitable for live streaming. Yeah.
Cool.
Yeah. I should have, because I provided this as a global using before. It should be.
Do you want to try again?
Nah, let's maybe we can redeem ourselves at the end. Yeah.
The bonus time for later.
Yeah.
Okay, so I'm gonna access the individual members, and I'm gonna access the first and the last one. Well, the first one with index 0, and for the last, I'm gonna take the from end syntax. So I'm gonna do caret 1. Caret 1 is the last item. Caret 2 the second to last, and alarm. So on and so forth. And the interesting thing about it is that when I hover this is of type index, which is interesting.
That's the pizza.
Because list does actually not have an index-based indexer. It has an int-based indexer only. But this compiles, and when I run it, this should also print the correct numbers. And it does, first and last, 0 and 4.
0 and 4.
Yeah, my mouse just left me as well. Can we see it? Oh, here it is. Here it is. Here it is. So we get the right stuff printed to the console. Wonderful. But yeah, it's still of type index. So how does this actually work? And when we look under the hood, we can see what the compiler makes of it. And so what it does, it kind of calls, so if we look right here, it calls list.count -1, and it indexes it that way. And this is how it works with an int-based indexer, even though it's of type index. Why -1? That's because it's after the caret. -2 would be caret 2, and so on and so forth. But unfortunately, when I use our list, I assume that I can't access it the same way. And yes, indeed, we get another error, a bit of non-compiling code, and that means little indexer duck for you. So can you extend our type to get to be indexing?
I'm not so sure
friendly.
anymore.
We're not so sure. We shall see. How's the confidence vote in the room? Okay, that's some thumbs up. Okay, we're still with you.
All right. So you've decompiled that we need an indexer. Okay.
Yes.
Let's see if I am capable of providing an indexer. Maybe I'm vibe coding too much. Who knows? So let's provide an int-based indexer. And we see the first problem has already disappeared. We could also provide a range-based indexer for both issues to disappear. I have the feeling we imported some very weird. Oh no, wait a second. Range. Yeah, I jumped ahead. I'm getting ahead indeed. What I meant is index. If we were providing an index-based indexer, both compiler errors would actually disappear because, well, 0 can be implicitly converted to an index, and the caret symbol is always a index. But this would be explicit indexing. Now we're going to do the implicit indexing pattern, with which we provide an int-based indexer. And there's an implementation detail. Let's just index forward into our list. But this only enables the int-based indexing. What about the caret-based indexing, which is the from and semantics? Eva has uncovered we need the count so that we can start from the end.
Yep.
So let's provide just that property. It returns an integer and is called count. And compilation is happy at call site already. Let's get the implementation details working as well. This code. And I'm not sure what this is calling here, but let's just run it. And we should now get the first and the last element. Excuse me. Yeah. So because I was missing the using, right? I thought I imported this as a global using. Apparently I haven't.
Yay. Oh my goodness. Okay.
Okay, there we. Thank you. And now we will use the implicit indexing to index into the first and the last element. I'm going to buy a new machine after this presentation, yes. So we do indeed get first and last of now our collection. As an implementation detail, there is not count is usually used for collections that can grow and shrink, like a list or a dictionary. What about fixed size collections like array, immutable array, and spans? They always have the same size during their lifetime. And the property for the length of these is called length. So when we have a count that may grow or shrink over the lifetime, length is always the same size. And the compiler is looking for both, either length or count. If both exist, the compiler is preferring length, but it shouldn't really have both, because that would mean this collection can be both of fixed size and growing and shrinking simultaneously, which doesn't make too much sense. But this is the pattern that the compiler is looking for.
Amazing. Now let's slice things up a little bit.
Did I earn this one?
Yes, you did. Yes, you did. Well done. Okay. So I want to go back to my for each, and I don't want to print the entire list this time. I only want to print numbers 1 and 2, and for that I'm going to use range. We also already got a little teaser from Stefan, and range. So if I hover this, we'll see that it's of type range. Why does it not hover? There it is. Range. Wonderful. And range has an inclusive start and an exclusive end. So we want to start at 1 inclusively and end at 3 exclusively. And that should give us 1 and 2. Hopefully. In about 15 minutes. 1 or 2 minutes. Wonderful. Yay. Cool. So that worked. Good job. Right. And now I want to see what happens in the IL view here. And we can see that we call another wonderful method here, slice. And this method is is part of another pattern, and it has 2 arguments. It has a start and then a length. And that's sort of how this works underneath the hood. And because we've just had this wonderful from end syntax, I'm gonna do caret 2 here. So we said caret 1 is the last item, caret 2 second to last. We're still in the range, so still exclusively. So we usually run this code like every 2 seconds when we do this talk, and it goes usually pretty quick. So I'm gonna run it real quick. I think I'm gonna build as much as I can from now on and not run it, and you just have to believe me. And so how does this look underneath the hood? So we still call this slice method, but that's a bit more complicated, or is it? I don't know, because the beginning is still we want to still start at 1, and then the length is calculated with so the caret syntax that we had before is actually still the same. So it's count this dot count -2 because we have 2 after the caret. Before we had -1, we had 1 after the caret, but we have another -1 here. Oh my goodness. Why is that? Because of course we don't want to start right at the beginning of the list. We also need to take this 0 into account. That is also not part of this length that we want for our slice method. So this is what the pattern looks like. And, well, I want our list to be able to do this as well. And here is your slicing duck, Stefan. Good luck.
Well, not only do I like slicing into collections and spans, I also like slices of pizza, but we'll be there in just a couple of minutes. All right. So we already have 2/3 of this pattern implemented. We do have the indexer. We also have the length required. Well, yeah, what I showed earlier already, I was jumping ahead. We could have a range here directly and have more or less explicit range-based indexing, but this is not the implicit pattern that we are looking for. And the 3rd piece of the puzzle that we need to add is the slice method. It's called exactly a slice, and you will find, for example, on span and read-only span, that's the core type, the core method to navigate and narrow the views of these spans, but also now of our list. So because we are narrowing the view, we're cutting off at the beginning and or at the end, we will return a new instance of our list. and provide those two arguments, the start and the length. String start. Thank you. And we see that at call site, the compilation already succeeds. So the compiler is now binding to slicing into with the getting the start from the index and getting the length via the from and semantics through our length that we provided here. So let's just get the implementation details working as well. Let's return a new instance of our list that we just, as an implementation detail, slice into the underlying list, start and length. Not every collection of the DCL has this slice method, but most. Let's provide a missing constructor. And this should not only satisfy the call site, but also the callee. And now we index into our collection, or we actually get a subrange, a few into our collection, only containing index 1 and 2.
Awesome. That's duck is well earned.
Oh yeah.
Yes. That can go over there. Okay, cool. The next pattern is actually maybe potentially my favorite because it's the one that I learned first, and it's the for each pattern. Now we know that we can for each both list and our list because we've been doing it for the entire talk. But obviously we are implementing the IEnumerable interface here. Now the for each pattern does not actually need this interface. Link heavily relies on it, but we're not linking today. So actually, I can just get rid of it. And then something down here doesn't compile. I'll also just get rid of that too. Wonderful. Well, no, the code still compiles. And when I run it, well, we're still in the range thing. I maybe should have gotten rid of that a little bit. And I also got rid of something. What's here? What? What?
So yeah, collection initialization doesn't work without the IEnumerable interface. You know what?
There we are.
We can do a little trick because we have a constructor that takes a list, which should be, if we do that, should work.
Oh, come on.
It's a bit indirect, but it will work.
All right, cool. Okay. Well, but then my whole spiel about it still works and everything. I did just run, didn't I? Oh yeah, I did. Doesn't work.
Does it though?
My beautiful for each pattern.
No, it should still work, but we are initializing our collection. I think that's just a rendering. Come on. Yes. Oh my God.
All right. Well, I can.
Also, now it's ambiguous between. Damn it. Excuse me? Between, probably. Oh, yes, indeed. Very good. Because we have both a list and a span to connection initialize. Oh, yeah. Yeah, we had our entire presentation was building top of it. Yeah.
Yeah.
You should know. I hope.
Cool.
Okay.
So we can still print the items to the console. So for the for each, we know that there's a pattern, and somehow we're already matching it, matching the shape. And if I scroll down here, well, this get enumerator method looks very, very suspicious. My money is on that, so that's what I'm going to look out for when we go into our IL view. And I can actually see, wait, oh, well, it's right on the far right-hand side. We actually do call get enumerator right here. And this returns an enumerator that has a bool returning move next. And while move next is true, we can access this current here. And yeah, and then finally we also dispose. And so then this is the whole for each pattern. So we need an accessible parameterless get enumerator method that returns a type that has a bool returning move next method and a property that's called current with at least a get accessor because we need to get it right here. And well, I already spotted the get enumerator method. And well, we are returning the I enumerator, which I suppose has these other building blocks that we need. Now, Stefan, do you think we could write our own enumerator?
10 minutes ago, I would have said yes. Now I say maybe. All right, so we have uncovered the pattern. So let's implement just that. We need to provide our own custom, our enumerator. So let's create ourselves. Usually enumerators, if you look at the list, the enumerator in the list is a nested type. This is usually the pattern. So let's provide our enumerator also as a nested type. I will use a ref struct because as an implementation detail, I want to use a span, and only a ref struct can have span fields. Let's have our enumerator. We don't need to make this generic because with the list, the outer type, the nesting type is already generic. So this is implicitly generic. And now let's provide the methods that we need. Of two, we have a bool returning move next method that doesn't take any arguments, and the current property that returns the element of this collection. In our case, it's generic, therefore T, called current. Now we see up here there's no more red, so at call site, for each is already satisfied. Now let's get the implementation detail working as well so that we can actually run it. I mentioned I want to use a span under the hood. So we'll just do a bit of implementation detail logic so we can actually run it. We will pass in the underlying list that actually contains the elements. We will use collection marshal to get the underlying memory as a span. This is with currently C#14, this is not marked as unsafe. With C#15, this may be unsafe, and we need to put this in the unsafe block, but not yet. Then for every time we move next, our enumerator is a state machine. So for every move next, for every iteration, we advance that state machine. So we need a state. For our enumerators, it's usually an index. We will start with the index of -1, which means that the iterator hasn't started yet. And then for every time we call move next, we will advance the iterator or this index. And then we need to check, well, if we only increment into infinity, we have an infinite loop. So we need to know when to stop, which will be when we reached the same index as the length of the underlying collection, -1. So when there are no more elements in that collection, then we should stop. So we check against the length of the underlying collection, and we will return true if we are still within bounds, and we will return false when we are out of bounds and are meant to stop. So let's just, for the current, in order to actually extract the current item index with the index that we are calculating into the span, and this should complete the implementation detail as well. And now, fingers crossed,
Fingers crossed.
we should now be able to iterate through our list, although it does not implement the IEnumerable interface, because we satisfy the get enumerator pattern, which returns a type that has move next and get current.
Awesome. Well, but not quite so fast. I want to also check underneath the hood. So I'm going to just close this, go to the IHEL view. All right, I see the enumerator. We so-called get enumerator here. And underneath the hood, it looks pretty much the same. So we have, move next. We've got current here. But one thing that I'm missing is the dispose right at the end. So that's not well, as everybody can see, it's not technically part of the pattern. It works without it, but it is best practice to have it. So maybe let's add that as well.
All right, so let us make our enumerator disposable. Let's implement the iDisposable interface. Let's implement the method. And when we call dispose for evidence, let's print disposed.
Okay.
And this should now iterate through 5 through 9 and then print disposed as well, being evidence that we have this try finally dispose pattern successfully automatically implemented.
Awesome. But also I see that we're using refstruct, and they were actually only able to implement interfaces since I think C# 13.
Right.
So what if we're working with an older version?
So if we go back in time, let's lower. Currently we are on .NET 10, where the default language version is C# 14. Let's go back in time and say language version is 12. Now this will stop compiling, because with at C# 12 time, well, it will take a while to catch up, but we will get an underlying soon saying refstructs cannot implement interfaces. This was a feature added in C# 13. Yes, and there we go. Now saying, okay, use C# 13 or greater. So how do we now make this disposable pattern working? Maybe.
Oh. It compiles when you just remove it. That's pretty cool.
It does. Let's see, even if without the iEnumerable interface, it would print disposed at the end.
Yes, it does.
It does.
That looks like a pattern to me. Do you think this is possible with any kind of type?
It actually, let's short circuit this a little bit. It actually is not. So the dispose pattern, even if you have a using declaration or using statement, this dispose pattern only works for refstructs, because at the time that refstructs were introduced, they weren't able to implement interfaces. So the compiler is recognizing the dispose method on refstructs as the disposing pattern, but not on regular structs and also not on classes.
All right. Well, we've gone from building collections to iterating them. I think we are ready for some async and await magic now. So I'm going to await this for each. I'm going to have here a method called get items async. And down here, I'm just going to declare a static async in of int returning method get items async. Wonderful, wonderful, wonderful. And in here, okay, I'm gonna have a for loop with an upper of 5, and in here I'm just gonna await a task dot delay 500 milliseconds, and then I'm just gonna yield return hi. Perfect, amazing, cool. So fingers crossed, when we run this, we should get some items printed on the console, hopefully with half a second delay. Half a second plus.
There you go.
Oh, 1, 2, 3, 4. Yes, awesome. So that worked. That's good news. Now let's have a look what's happening underneath the hood. Oops. Nothing to show. All right. Okay, so we're definitely in the async state machine now. So everything looks a little bit more, I don't know, busy. But I think we can see some familiar faces. For example, I can see get async enumerator. So we just had get enumerator, get async enumerator here. Then we also see move next async. We had move next, now it's moves next async. And when I scroll down, well, we find a trusty current here as well. Obviously, that's not async because it's a property and they are not async. But these shapes, so get get async enumerator, move next async, and the current property, these shapes are not accidental. They're actually the async equivalent of the foreach pattern. And well, as always, when I have a new pattern, I want our list to have the exact same behavior. So can you please update our list with the async enumerator pattern?
Async await and the async state machine. That is quite a rabbit hole that I dove in one too many times. So yeah, I'm regaining some confidence now. All right, so we currently have the synchronous for each. Now let's go into the asynchronous for each. I don't want to eliminate any of our existing behavior, so I'm going to duplicate from what we have so far. Duplicating the synchronous get enumerator method and just adding asyncs here and there. So it's now get async enumerator, and it must return a different type that we will call our async enumerator. Now let's duplicate our enumerator type here as well and rename it into our async enumerator, which now should fit the async pattern. Now we can't use ref structs anymore because ref structs, they always must live on the stack. But when we have async and await, there may be threading involved. And yeah, each thread has its own stack. So the memory model wouldn't work that way. So we need to promote this to the heap. So our enumerator here needs to be a class. Now we can't use span anymore. So I'm just gonna fall back to the good old heap allocated array. Just an implementation detail. Let's get the array out of our list. And then for the rest, we'll just implement with now asyncify our synchronous enumerator. So move next is turning into move next async. And instead of a bool, it needs to return something that is awaitable, returning a bool. We'll use a value task here, value task of t, value task of bool. Now we can make this method asynchronous and add the same delay that you have added of 500 milliseconds. And the current property, as you mentioned, will remain the same. Properties cannot be asynchronous. And we should have now emulated the very same behavior, but with our list is not only foreachable, but also asynchronously foreachable. And after it compiled, it will run gladly.
Yeah, well, maybe we can talk about dispose async while we're waiting.
Well, let's actually do that, yes. Because what we will see is that dispose at the end will not be called. Well, okay, it's coming along.
Woohoo!
3, 6, 7, 8, 9.
Perfect.
But yeah, the dispose indeed is missing. Now we would give it a try whether async disposal was a pattern. So we jump to our asynchronous enumerator. We could now add the I async disposable, which is the asynchronous version of the I disposable. We would be not patient enough and add the missing member. Now this is very similar to the synchronous dispose, but just instead of void, returning a value task. So let's print disposed async here. Of course, this needs to be an asynchronous, or it needs to return something. So let's make this method now async. Let's also do a task dot delay of maybe 1 second. We do not return this here. And we can now run this. And even if I wouldn't have added the I async disposable, with or without, we will get the disposed async. Because unlike the synchronous disposal, asynchronous disposal is a pattern for every type. So if we implement the interface on a class, a struct, or a ref struct, it will be recognized by the compiler as a pattern.
Amazing. Cool. All right. Now I get to delete everything. Wonderful. Oops. If I can do it. And I want to have just a very, very simple await example here for you. So I'm just going to do, well, let's have before, and then I'll have date, time, off, set, dot now. Wow, it's the first time I'm typing faster than the autocompletion. This is like a premiere for me. Oh my goodness, and there's so many things. Okay, and just gonna duplicate this. And here I'm just gonna have after, and then in between, I'm gonna await another task.delay. And here I'm gonna put in time span. No, this was not. This is like this, right? Oh. Right? From seconds, we don't have.
No, but it's right, yeah.
Oh my goodness.
No auto-completion.
From seconds. And then.
Yeah.
What? No, on stream. Why? What am I doing? Ah, no.
Oh. I think you just need to catch up.
Oh my goodness, this is playing tricks on me. This is scary for me. Right. And let's run it. And I only put in 2 seconds. Usually we put in like 4 or something crazy, but you know, I'm being aware of everybody's time today. And we get before and after, amazing, with these 2 seconds delay. Now let's have another look underneath the hood. And again, there's so much going on here. And when I first started, I was like, I don't understand anything. So what I like to do is I kind of look at stuff that I definitely sort of recognize from my code on the left-hand side. Like, for example, the before and the after. So I know everything else happens in between. And I can see the task delay here. And now I kind of get a glimpse of the pattern that is hiding right here. For example, the get awaiter is being called here. And then on this awaiter that we get out of that, we have is completed. And if the awaiter is not completed, then we record the state here. And we can also see that we have this method await unsafe on completed that we, I did it again, didn't I? I'm going to have to remove some of this because I need to scroll to the left-hand side to show you something wonderful. So on the async method builder here, we have await unsafe on completed, and we pass the awaiter here as a reference. And now that tells us that we need to implement one of 2 interfaces, the iNotifyCompletion or the iCriticalNotifyCompletion interfaces. And then, yeah, eventually when the awaiter is completed, we get the result down here. So what this pattern, what I sort of want to draw your attention to is get awaiter method, the is completed, the fact that we pass the awaiter as a ref to the async method builder, await unsafe on completed here, and the get result at the end. And with this wonderful pattern, you can await anything. Even the pizza. And for example, if I just get rid of this here, I can just await time span. Can't I, Stefan? Can you please extend this wonderful type to make it awaitable?
I have this almost deja vu ever. Well, actually not a deja vu, but a flashback, because 6 years ago when I did my very first public talk, it was at the .NET Devs RT meetup, and I was talking about everything that you do not want to know about async and await, and this was a part of it. So it's still haunting me. All right, let's see if I can still get it right. Now we need the get awaiter method on time span. Now we run into a problem. This time span is not owned by us. We cannot add an instance method to time span, but we can add an extension method. Now let's use the new C#14 extension extension members for that, but we need to go back to the future. We're still on C#12. Let's go back to C#14, or let's remove it all together. So we are now up to date and can use extension members. So we need a container type for our extension method, and provide an accessible method that is called getAwaiter. Actually, this one is not static because I was missing the extension block. So let's do extension. We are extending time span. So the receiver type is a time span. Here now we put our getAwaiter method, and our getAwaiter method should return something that is awaitable. And as a matter of fact, the task awaiter just does that. Now we see compilation already at call site is satisfied. The pattern is satisfied. Let's now get implementation details right. So let's return a task.delay where we pass in the time span that we have captured and get the awaiter from over there. Excuse me. This is again the pizza place. Should I pick up? Do you want to take my? Okay. Interesting. Wonderful. Now, when we would run this,
Yes.
it would definitely work the same because it has it 7 times. This would wait 2 seconds and then print after as well.
All right, but we're still using the built-in task awaiter. Do you think we can also write our own awaiter?
Interesting. I'm not in. Yeah, next time I'm gonna call it. Sorry.
Yeah, I want my own awaiter. I don't want task
Want your
awaiter.
Own awaiter. Okay.
Yes, please.
Let's do just that. So instead of the task awaiter, let's use our awaiter.
Yes.
So we have to provide our own awaiter. So let's provide our awaiter. We're not using we need the free methods. We need the free members. We need the property, a bool returning property that's called is completed.
Yep.
Okay, excuse me. Yes, bitte. Pizza. Okay. We need the is completed property, and we need to implement either the I-notify completion interface or the I-critical notify completion interface, where the I-critical notify completion interface actually is implementing the I-notify completion interface as well, depending, those are 2 different variants of how the execution context flows or doesn't flow, and then the compiler can choose the right thing to do. So in this case, we will now implement both. And the last piece of the puzzle is the get result method.
Yes.
So let's provide a void get result method.
Mm-hmm.
And now let's just actually return a new awaiter here, a new our awaiter.
Cool.
And at call site, again, is still satisfied, although we use our very custom awaiter now. And yeah, let's get the implementation detail actually working so we can run it and see the delay. So let's provide a time span here. Let's capture a task awaiter. Task not delay. Pizza. Time span. Now I want to slice again. Get awaiter. And we will just forward to this awaiter because implementing your own awaiter is quite complex to get right. So we will fall back to the existing variant of the VCL. Get result, although it is void, it's called get result, but it's void. That's kind of weird. In this case, if an exception occurs during the asynchronous execution, get result will rethrow that. Then the only pieces missing is the onCompleted, as well as the unsafe onCompleted, passing those continuations. A continuation is essentially a block of code that occurs after an await, if at the time of the await, this awaitable was not completed yet. Anyway, this should now satisfy also the one-time experience, and we should have, with our custom awaitable that fulfills the pattern, now get a 2-second delay.
And after, awesome. That's pretty cool. But you said the get result is a bit weird that it's void, right? So maybe let's make it not void. But what if we like return something? So I kind of imagine something like time span like delay. Oh my God, what happened? What happened?
Don't worry about it.
Loads of breakpoints. That's good. And also, what? Yes, okay, it doesn't compile, that's fine. Let's also just print the delay at the end to make it a little bit more visible. Do you think we can do that?
Yes, because just as the current in an iterator or in an enumerator is declaring the return type, the get result is also declaring the return type of an await. So if the get result is void, await does not produce a value. But if we want to produce a value, the get result must be non-void. We want to produce a time span, hence we go down to the get result, return a time span, and actually let's return our very time span here that we have captured. And running this now will yield the very same behavior, except we now return the delay as well, and should see then after 2 seconds, 2 seconds on the screen.
Amazing. Well earned, duck. All right. And please make sure that you press submit on your quiz now, because you should have everything you need to answer all of the questions now. And we've got some pretty cool prizes for the winners. The time is also recorded. So even if you get all of them right, somebody might have been quicker than you. So don't be sad about that. And while you're pressing submit and filling out your final questions, we've got some more patterns for you, because by now you'll probably see patterns everywhere. For example, the async method builder.
We'll just briefly go through this pattern. Now I'm going to do the same that you did earlier, just delete everything.
Yes.
That does feel good.
That's good, isn't it?
So we have more patterns. .one async. We should wait this expression, navigate into, it's getting ready. And you can either your awaitable or a method you can attribute via the async method builder. What we saw earlier is in this async state machine that gets created, not only your custom awaiter is a part of that, but also the async method builder. So if we were to take a look at the decompiled code, with that, we no longer use the default from the .NET team provided method builder, but we can actually use our very own method builder. Well, why would we need that? For example, this is how value task works. Value task was introduced way after the regular reference type based task. And this one has the async method builder in order to provide a very high performance implementation. With a bit of a caveat, there is some caching going on under the hood. And since resources may be reused, you are only allowed to await a value task once. But this is how the .NET team implemented it. But also with .NET 11 now on the horizon and the runtime based async, you may not need to worry about this anymore, unless you still want to support all the target frameworks.
Yeah, exactly. And another pattern that you might have spotted throughout the talk is the interpolated string handler. That's also, yeah, a bonus pattern that we have for you.
So whenever you have with, what's this C#8? No, I'm mixing up versions now. Previously, when you had an interpolated string with the dollar and then some interpolation holes with the braces syntax, you were getting a string.format or a string.combine, I think. Now, with a modern version of the compiler, you get a default interpolated string handler, which is calling for every string in this interpolated string. It's called append literal. And for every hole that you are filling, you are calling append format. And by providing, you could provide your own interpolated string handler that is then used instead of the default one if it provides the pattern. You actually can see this. I think this is, for example, in debug.assert. We can say true, then pass some string. And of course, debug, that's in system dot, I forgot. Compiler services, no, system dot diagnostics. Something is wrong with the global usings. No, there we go. Anyway, let's jump into there. And the team here is providing a custom so-called assert interpolated string handler, because you own this message when you have a debug assert at debug time being false, then this message is printed as an error. But if the condition is true, then you don't need this string.
Yeah.
So as a performance optimization, this string is only evaluated and created into a string if the condition is true and if the condition is false. If it's true, then essentially nothing is done. So this is how you could provide more efficient custom string creation logic with that pattern.
Awesome. And yeah, obviously the language is always evolving. So hopefully, fingers crossed, with C#15, we should get dictionary expressions. So that will be another pattern. But not everything is actually an extendable pattern like the ones we showed you today. For example, the log type that was introduced in .NET 9. So it looks exactly like the patterns that we showed you today, but it really only works with system.threading.lock. Even if you build your own custom type and you match the shape exactly, it will still fall back to the default monitor-based synchronization. Yeah, and I guess with that, if you want to learn more or follow us on any of your preferred social medias, we've got a little QR code, I believe, for you. So again, phones out, like and subscribe. Yeah, there should be all of the contact details right there. And yeah, I guess while I'm sort of trying to figure out who won today's quiz, we have a few minutes for some questions as well.
Are there some questions before we slice into the pizza?
Some questions in the audience? Stop.
Two of us are just thinking how often have you implement such a thing in your usual work?
The enumerate, not all too often, to be fair. I will just briefly refresh the quiz so that Eva will find that. I think you need to click here so that this is happening. Well, actually, as a matter of fact, I currently have a branch at Sentry where I work at, where we are experimenting with our logging solution to use a custom, we call it the log interpolated string handler, so that you can use, because with the Microsoft extension-based logging, you should use the standard with the braces 0, 1, 2, 3 syntax, and then pass in the arguments as an array at the end. And well, it would be some nice syntactic sugar if you could actually use interpolated strings while still having structured logging enabled. And for that, we are exactly fulfilling that pattern. So we have our own interpolated string handler that has these append formatted and append literal methods. And for that, we can very much use it. So I guess if you, for library authors, these patterns can come in very handy. For application authors, I guess you won't really need them all too much unless stuff goes wrong. So if, for example, you have a for each loop and you get an exception, in the call stack, you will see move next. But maybe you have never written move next yourself. Where it is coming from? It's from the pattern the compiler is lowering to. So you may not need it actively, but you encounter it passively all of the time.
Okay, good to know. Thank you.
Which other questions can they both answer? There are no questions on stream. On here.
Does this pattern support the concurrency in, for example, in parallel tasks or anything in the parallel process?
Which pattern?
The pattern that you have implemented for a list or something like this.
Like the for each?
Out list pattern, out list class.
Out list. I'm sorry, I'm
The
Yeah,
class
quite
that
sorry.
its name was outlist.
Our list. Oh,
Yeah, sorry,
Oh.
sorry, outlist.
So the which one? We had the indexer, we had the range, we had the enumerator. Which one?
Totally, if it's
In
async.
general.
Yeah.
Well, no, in general, it's just because the compiler is just changing the syntactic sugar it has essentially to call then those methods that are recognized by the compiler via that pattern, but they are not thread safe per default. But an iterator usually, if you have just one for each, this will not be accessed concurrently. So you can't really. There may be maybe there is a way you can do it kind of wrong, and then there may be a foot gun here and there, but per default you don't need to for these patterns that we discovered, or for the collection-based patterns you don't need to worry about synchronization because that should be part of the pattern, unless you go into the async enumeration, do something wrong there. If you have a custom awaitable or a custom method builder, those are tough to implement. You could get something wrong there and then mess up your concurrency.
There's one comment in the stream about custom awaiters, that with .NET 11 there's already cited unions. Not only unions. Yeah. The comment says, thinking this will change drastically the things like custom awaiter and the way we build types with discriminated unions was it's coming.
I'm not sure. I think those are two things, right? So for when it comes to asynchrony, one-time async will change drastically. Currently, the entire async state machine is compiler generated. If you have an asynchronous call stack, you will see move next and is completed all over the place. In .NET 11 Preview 2, now there is something called one-time async, for which now the runtime is aware of asynchrony. So the compiler will not be emitting this state machines, but this is all handled at runtime, and the runtime knows how to optimize code most efficiently. So for if this is currently in preview, it may be released with .NET 11, maybe not, but once this feature is released, then yes, custom awaiters, you won't be able to, you won't need, it's very unlikely that you're gonna need a custom awaiter for performance optimizations, but for .NET 10 and less, well, you still need, in some cases.
Other questions? Last one before Peter gets cold.
One final one.
One final one. So here you are.
Okay, for the last one, let's say you introduce for people like me, like very new to this topic, who have like not really used that at my work. So what kind of pattern that if I start to learn, where should I start?
Well, I guess you need when starting, this is definitely an advanced topic. It goes into how the compiler works under the hood. So when you're starting, yeah, you're not gonna really need it. But it's still, as mentioned earlier, it's still good to keep in mind that sometimes code gets rewritten by the compiler, and then in particular with call stacks, because this is how you usually observe your code then, or when you debug, your code might look a little bit differently than you actually wrote. So I think it's nice to keep in mind what capabilities the compiler has to rewrite your code. But again, that's more of a passive usage than an active usage. When you get more later on, more into library authoring, as I'm right now, then those patterns become more interesting to actually actively implement.
All right, thank you. Yes.
Right, and I think we also have some winners on the quiz, unless there's some chat questions.
No, nothing new on chat.
Cool. Okay, so we've got on third place, we've got Nick. Woo! On second place, and by the way, you all have 10 points, so you all have everything right. On second place, we've got Greg Stack. Woo! And on first place, we've got Manuel M. Yes! If you heard your name, please stick around just after. We've got some awesome Century swag for you. Thanks again for Century for sponsoring us. Thanks for .NET Devs for having us. And obviously, thank you to you all for spending the evening with us. You've been a wonderful audience.